Hey everyone, so we're going to end up solving this problem again. I've already solved it once, we've got like 0.8 meters. I want to solve it again, but this time I want to solve it graphically. I think solving it graphically is prettier than solving it algebraically. And what can I say? I like aesthetics. So what we're going to be doing is we're going to be going back looking at our graphs from before and seeing if we can use those to do the same thing. So the method with which we're going to use is not that different. We're still going to go ahead and use this information, use our vertical information to solve for the amount of time, and then use the time to solve for the thing that we're looking for, this horizontal position. So that shouldn't be too bad. So I'm going to go down and look here at my velocity versus time graphs. These are always probably where you want to go. I'd expect you to be able to draw any of these graphs, but the velocity versus time graphs are the ones that are the most useful to us. Specifically, let's zoom in and look at the horizontal part. So let's think about what this is saying. First off, we note this starts off at a velocity of 0.513 meters per second. It's initially moving in the positive direction. That means the ball moves upwards. And in fact, we should be able to figure out how far it moves upwards from the area of that triangle. Then it falls back down. That's what we're going to see here in the second half. And our goal is to figure out at what time will it have fallen all the way back down to the ground. Then we'll bring that time here. We know that this is 1.41 meters per second. And if we can figure out how much time before it hits the ground, we should be able to figure out this area here. And this area should give us our answer. All right, the only other piece of information we really need is we know that this total area here, the area of this triangle plus the area of this triangle, has to add up to negative 1.3. So why negative 1.3? Well, let's look back at our problem. We have a ramp. We start off at 1.3 meters above the ground, and we want to know when it hits. It's first going to go up for a little bit, and then it's going to drop. We need it in total for it to have gone down by 1.3. So looking back at our graphs, the total area will end up being 1.3. So let's see what we can solve here. I'm going to switch over to another color, hopefully one that's easy for you guys to read. So we'll switch over here. Switch over here to another color and see what we know. We know how tall this triangle is, but we don't know how wide this triangle is. So I'm going to call the width of this triangle some time t. And because we're probably going to have some other time t here, I'm going to call this one t1 and this one t2. If you'd rather use x, y, a, b, that's fine. Well, the area of this triangle we know is 1/2 base times height. I know how tall it is. I just don't know the base. But here's something I know. I know that the acceleration this whole time is negative 10 meters per second squared. That means that this triangle has to be 10 times taller than it is wide. So this height is 10 times bigger than this width. So that means that this t must be 10 times smaller than 0.513. So this must be 0.0513 seconds. Hey, look. Now I know the base and the height of my triangle. So base and height of my triangle, we know that it's 1/2 the base, 0.513 seconds, times the height. Oh, sorry, 0.513 meters per second. That's the height, actually. And then the base, 0.0513 seconds. So when I go ahead and I throw that in my calculator, which I keep forgetting to turn off and having to redo the video, whatever, I end up getting, so let's go ahead and start this over, 0.513, 0.0513. So the base times the height is that, and then we did need to divide it by 2. 0.013158545. I'm going to round that to 0.0132. 0.0132. So that means the distance that it travels upwards after it goes off the ramp is a little over a centimeter. That seems reasonable. It's not a very steep ramp. I can see the ball only going up a little over a centimeter. So that means that when it falls back down, it has to fall a little bit further than 1.3 meters. This area right here has to be big enough to account for both motions. It has to account for the fact that it needs to drop 1.3 meters and it had already gone up 0.0132 meters. That means the area of this triangle must be 1.332 meters. Does need to be negative. You guys probably can't see that. Let me switch over to a more visible color. So negative 1.3132 meters. That has to be the area of this triangle. Why? Because there's no other way for this thing to hit the ground. So I have a triangle. I don't know how wide it is. I don't know how tall it is, but I do know the area. But remember the other thing we know. We know that this triangle must be 10 times taller than it is wide. Or in this specific case, negative 10 times taller than it is wide. If the width is T2, whatever that is, the height must be 10 times bigger than that. So that means 1/2 base times height, 1/2 the base, this T2, times the height, negative 10 T2, must be equal to 1.3132 meters negative. Solving that out, we end up getting, well, let's run through it real fast. Solving that out, we're going to end up getting that T2 squared is equal to 1.3132 meters over 5 meters per second squared, technically. So T2 then must be equal to, time to turn on my calculator and forget to turn it back off. I have to redo the video. So we know that that's the whole thing. Let's go ahead and divide that by 5 and then take the square root. I get 0.512 seconds. Now, that's not the whole time. We have to add to it our other time, this time right here. So we're going to have to add that 0.0513 to get the total time. So if the, so let's go back. If this time right here, if it's in the air here for 0.512, that means the total time from beginning to end must be 0.5634. So I remember to turn off my calculator. Good job. All right, don't get me wrong, that's a lot of math. And actually, if you go through and look at the actual numbers we typed in and all the things we wrote, we actually did the entire quadratic formula. Crazy, right? Like, that whole thing was us just doing the math without the quadratic formula. You are welcome to use the quadratic formula. It gets you the same thing. That's the same answer we got from last time. But, you know, why not? All right, so let's move on and now solve over here. We know now that if this thing lands at 0.564. This must land at 0.564 seconds. So we have a rectangle. We know that it's 1.41 meters per second tall, 0.564 seconds wide, 1.41 meters per second, 0.564 seconds. Turn on the calculator again. I end up getting 0.795, or 0.79, I think is where we'll end up rounding at. Which, you guys probably can't read that, 0.79 meters, which is the same answer that we got last time. Hey, what do you know? Math works. All right. Again, this is just what I like to do. I like solving things graphically. I think it's pretty, I think it's fun, I think it's interesting, and I can remember how to do a triangle more than I can remember how to do the quadratic formula. Like, don't get me wrong, I remember the quadratic formula, but I don't always trust my math for it. Now, I do allow you to use Desmos. I will allow you to use a graphing calculator to do stuff like that. I think that's fine, but I would ask you to show me whatever graph you used if you did solve for something like that. All right, so just a quick reiteration of what we just did. All I did was looked at the graphs we made from earlier. I figured out how much time it would take for the ball to hit the ground using the graph over here, the vertical velocity graph. We know that that gives us the amount of time that this takes, and then we applied that time to our horizontal velocity graph to figure out the area under the curve there. Let me know if you have any questions. Let me know if there's anything else you think I should cover on this problem. I think I've gotten most of it. We might, just as a bonus, try to figure out what the angle was to hit the ground, but I'm not going to do that right now. Let me know if you have any questions. Let me know if you need anything. I'll be on Classroom. I'll be on my email. I'll be in and out of the Discord. I'd love to talk to you guys. All right, everyone. Have yourself a great day.